Hello, people. We're going to talk a little bit here about some fundamentals of trigonometry. All right, we're going to use some simple trigonometry in physics, and I understand that some of us need a little bit of a better introduction to that, or an introduction at all. So, trigonometry is really about can I change the, really about, well, triangles, kind of, and really about some ratios. That's the most important thing. It's about some different ratios. So let's take this triangle here. Not that triangle there, because I don't want that triangle. Undo, and give me that. Good. Now, this triangle has three sides. Yeah, they all do. And if we look at an angle here that we're going to call theta, there are, well, the three sides are in what we call special locations relative to that angle. Okay, since this is a right triangle, well, all right triangles have what we call a hypotenuse. And since this side over here is, well, the farthest away from the angle, or really, it's on the opposite side of the triangle from the angle. We call this side the opposite. All right? This side over here, since it's right next to the angle, but it's not the hypotenuse, we call this one the adjacent. Adjacent meaning right next to. Okay? If we took the same triangle, let's clone this, please. Let's take the same triangle, but look at a different angle. If we looked at this angle, theta, up here, well, this would still be the hypotenuse. The hypotenuse is always the long side across from the 90-degree angle. Now, the angle, or sorry, the side on, well, the side over here is no longer this same adjacent. Because the angle's in a different place, this side is now the opposite side from that angle, all the way across the triangle. This side here, next to the angle, but not the hypotenuse, is now our adjacent. So it matters a bunch which angle you're talking about when you identify the name of a side. Okay, for us, in most cases, we're going to deal with angles that are measured relative to the horizontal, like this one. Okay? Now, we have this triangle. Okay? What people noticed at some point was that if we had a triangle with the same angles in it, hopefully we can tell that this angle theta here and this angle theta here are the same angle. Well, if we look at the length of the opposite side, which I'll just abbreviate as opposite, OPP, and I'll abbreviate this one as adjacent, and I'll abbreviate this one as hypotenuse. Well, this one also has an opposite, smaller, but it's there. It has a hypotenuse, smaller, but it's there. It has an adjacent, ditto. There are some ratios. There are ratios of the length of one side to the length of the other side. Or, for example, we can say, notice that this side length is less than this side length. But if we took, for example, the length of the opposite divided by the length of the hypotenuse, it would be the same thing as if we looked at the length of the opposite and divided by the length of the hypotenuse here. These two things, would be equal. And that's because that angle and that angle are the same thing. The same thing goes for other ratios. We could look, well, really there are three ratios. You can either talk about opposite over hypotenuse, you can talk about, adjacent over hypotenuse, or you can talk about, let me move these up a little bit, or you can talk about opposite over adjacent. Now, why couldn't you talk about adjacent over opposite? Don't worry about that. So there are three ratios that talk about how the side of one triangle compares, the length of the side of one triangle compares to the length of the side of a different side of that triangle. All right? And this ratio we define to be something we call sine. Or in this case, we say that the angle theta has a sine, or there's something called the sine of theta, that by definition is equal to the ratio of the lengths of two sides, in this case, the opposite and the hypotenuse. And this ratio here, the length of the adjacent side divided by the length of the hypotenuse, we call that the cosine of theta. I don't know where those words came from, who cares? And this one, by definition, we call the tangent of theta. Might as well make this blue, right? And again, the idea is that, let's look at sines of this angle and this angle. All right? Remember, we said that if we look at this length divided by that one and this length divided by that one, those ratios are going to be the same thing, even though the triangles are different shapes, because this angle is the same angle as that one. Because those angles are the same, the ratio of the lengths of the sides have to be the same thing. I think that means they're similar triangles. Okay? And so someone then made what we call a mnemonic device out of this. And they said, since sine is defined to be that ratio, and cosine is defined to be that ratio, and tangent is defined to be that ratio, we can sort of abbreviate this as sine is defined to be opposite over hypotenuse. Cosine is defined to be adjacent over or divided by hypotenuse. Tangent is defined to be opposite over adjacent. And so people say SOHCAHTOA. So that's really it. And this shows us, for example, we can apply this. Let's take this. Clone. No, not clone. Undo. Undo. Copy. Next page. Paste. Let's look at a couple of examples. If we have, these don't need to be vectors, but for us they will be in a lot of cases. If we do a plain old, boring, non-contextual math example, we could say that if this is, for example, a 30-degree angle, well, if you type in the sine of 30 degrees on your calculator and you're in degree mode, you're going to get 0.5. And what that means is, well, by definition, since that means the ratio, this is opposite over hypotenuse, that means that opposite over hypotenuse has to have a ratio, or has to equal, that ratio has to equal 0.5, or we'll just call it 1/2. 0.5, 1/2, same thing. Which says that if I do multiply both sides by the hypotenuse, the opposite has to be 1/2 the length of the hypotenuse. As long as this is a 30-degree angle, whatever length this is, it has to be half of that length. So, let's say the hypotenuse was, let's draw this same triangle, clone. but I'm going to, oh, you jerk. Let's move this down here too. And let's group these. Group. Notice, even if I made it like a smaller triangle, but still kept that 30-degree angle in there, let's say that this length, right, this is still 30. Let's say that this is 10. Well, since that's a 30-degree angle, and the ratio of the two sides has to be that, well, the opposite side has to be, by definition, half the hypotenuse. It's got to be 5. Right? If we take a different triangle, and it's you know, and it's that's bigger. It's that big. And we say, okay, this one is 16. Let's make it more of a physics example. These are vectors. Let's say this is a 16-pound force. Or there's a part of a force, what we call a component of a force, that pulls 16 pounds that way. And this is still a 30-degree angle. Well, the question is, how big is the whole force? Well, if this is a 30-degree angle, we know that this side, the hypotenuse, has to be twice as long as that upward component. That makes this 32 pounds. Okay? There are, of course, examples you could do with cosine. There are, of course, examples you could do with tangent. But if you're comfortable with this mnemonic device, that by definition, the sine of an angle is defined to be the opposite side divided by the hypotenuse, or the length of the opposite and the length of the hypotenuse, and the cosine of any angle theta is defined to be the adjacent length divided by the hypotenuse's length, and that the tangent of an angle is defined to be the length of the opposite divided by the length of the adjacent. Well, then we can do pretty well. Now, let me say this. There's one more thing that will tend to do with these. Let's group, and then let's copy. If we say that these are the definitions of those three trig functions, sine, cosine, and tangent, we should be able to also do something like this. Let me draw a different triangle, a different looking triangle. Let's say that we have this. Now notice, I'm always drawing right triangles, and trigonometry only works with right triangles because you're dealing with hypotenuses. Only right triangles have hypotenuses. So let's call this our angle theta. And let's say that we know that this side length is, I don't know, let's say 20. And let's call it 20 meters to make this more of like a physics example. And that means this is a vector that goes that way. And this is a vector that goes this way. Those two vectors are added tip to tail to give us this resultant vector up here that goes that way. Yes? And let's say that 20 meters is what we call, I don't know, dy, the y component of the total displacement. We call this dr, really, for resultant displacement. And let's say that the resultant displacement is 30 meters. Notice this side length here of the hypotenuse has to be longer than the side length of any other side. So saying it's 30 is reasonable. Well, we know two sides, which means that we can either use this or this or this because we know two sides and there's only one other unknown. In this case, we call this, again, the opposite side of the triangle. And this is, of course, the hypotenuse of the triangle. So that means we can use this idea. Since I know the opposite side and the hypotenuse. That means I can find the sine of the angle. And remember, all angles that are the same angle, like these two we said are the same angle, they all have the same sine. And if we can find the sine, and all angles have the same, all equal angles have the same sine, that means we must know what the angle is. And so we can actually find the angle itself. And what we do is we take what's called the inverse sine. Ah, crap. The inverse sine, there's a -1. So if the sine of theta is defined to be this ratio, then theta is defined to be what we call the inverse sine of that ratio. Or what I say is theta is an angle whose grammar's not my thing, whose sine is, well, in this case, well, sure, we'll just say opposite over hypotenuse. Or theta is an angle whose sine is, in this example, theta is an angle whose sine is opposite over hypotenuse. Theta is some angle whose sine is 2/3. I guess we could do this, right? There's only one angle whose sine is 2/3. There's only one angle, whose sine is 0.666666. Every other angle has a different sine. So what we do is, if you're in high school, when I was in high school, you take out a big piece of paper that has sine, cosine, tangent, 0, 1, 2, 3, 4, 5, 6, up to 90. And then it has a list of all the values. And you say, okay, I want this, blah, blah, blah. Or you pick up a calculator if you're living the modern age. And so we type into our calculator second sine, and that'll give you this, what looks like this, inverse sine, of parentheses 2 divided by 3. End parentheses. And we get, okay, well, that angle must be 41.8 degrees. Doesn't look like it in my drawing because I made a crappy drawing. But you can use trig functions to find angles if you know two sides. Or, like we showed before, you can use trig to find the length of one side if you know an angle and the other side. Or really, as long as you know two of the three things in any one of these relationships, you can find the third. All right? What I would do your best to get comfortable with and remember is that. SOHCAHTOA. And of course, what it means. What it means is the way more important thing. SOHCAHTOA means that the sine of an angle is defined to be that ratio. The cosine is defined to be that ratio. The tangent is defined to be that ratio. Oh boy. Okay? So that's a quick intro to trigonometry. Okay? Maybe a little more, whatever. There it is. I hope that helps. We'll use that a ton in physics. Okay? A ton. Okay, adios.